In this unit, we're going to look at several algorithms that improve upon a priori. One direction is to use the portion of main memory that the a priori algorithm doesn't need on the first pass, because all it's doing is counting singleton item sets. That is the PCY, or Park-Chen-Yu algorithm. We'll talk also about further extensions called multi-stage and multi-hash. All these extensions to a priori have the goal of minimizing the number of pairs that actually have to be counted on the second pass. Then we'll go in another direction. We'll accept that the result might not be accurate. That is, we'll allow the algorithm to fail to identify some of the frequent item sets. But we want to finish quickly, preferably in only one pass, or perhaps one pass and a little more. Several approaches of this type will also be discussed. Now, the essence of the PCY algorithm is to take advantage of the fact that if the set of items is modest in size, we have lots of space during the first pass that we don't seem to need. We can, in fact, do some counting that will give us a smaller candidate set of pairs. That will help us on the second pass, where the main memory is often the critical resource, since we don't have to store as many counts. Okay. What Park, Chen, and Yu suggested was that we could hash all pairs into a large number of buckets. However, these buckets do not hold the pairs themselves, just the count of how many baskets contain pairs that hash to that bucket. Thus, the space needed for a bucket is small. 4 bytes is surely sufficient, and we might get away with 2 bytes if the support threshold is less than 2 to the 16th. Notice that it is not possible to store in main memory all the pairs themselves. We're trying to avoid having to use some space for every possible pair in main memory. So in the first pass, when we read a basket, we not only increment the count for each of its items, as we did for the first pass of a priori, we also hash each pair that is contained in the basket. And for each resulting bucket, we increment its count by 1. Now let's call a bucket frequent if after the first pass we find that its count is at least equal to the support threshold. A bucket could become frequent simply because many pairs each contribute a little to its total count. We can't tell if that's the case because we only had room to remember the total, not the count of each individual pair that contributed to the bucket. But in the opposite case, we win. If a bucket is not frequent, then no pair that hashes to it could possibly be frequent. So on the second pass, we only need to count pairs that hash to a frequent bucket. And of course, the usual a priori trick works too. We only have to count a pair if both its members are frequent items. So here's the picture of PCY that I'd like you to have. Okay. On the first pass, we use a little space to count the items, and the rest of the space is devoted to these bucket counts. On the second pass, we keep a table of frequent items. That's just as we did for a priori. But we also summarize the results of hashing pairs on the first pass by what we'll call a bitmap. And that's this. For each bucket, the bitmap has one pair that says whether the bucket is frequent or not. So if this is a bucket, and if it has a count, let's say that it's s plus 1, it's frequent, then it corresponds to some bit here that's a 1. Okay, another bucket that has a count, let's say s minus 100, that's not frequent, so it would get, its corresponding bit would be a 0. Okay, if the buckets are, say, 4 bytes, then we get a 32 to 1 compression, and yet we have all the information we need for the second pass, which is the bucket frequent or not? Thus, we have almost as much space on the second pass to count candidate pairs as we would for a priori. That's, of course, this area. But we hope that because the bucket counts will eliminate most of the candidates that a priori would have to handle, there will be many fewer pairs to count on the second pass. If that is the case, then the PCY algorithm might be able to operate in main memory on the second pass, while a priori would run out of space or have to use disk. On pass 1, we use what space we need to count the occurrences of each item just as a priori does. Typically 4 bytes per item will do nicely. But the difference is that whatever space we do not need for counting items is given over to as large a hash table as we can, where each bucket is a count, typically a 4-byte integer as well. So here's the pseudocode for the first pass of the PCY algorithm. We read each basket once, as we would on any pass of any algorithm. Well, we look at each item in the basket and add 1 to its count. Okay, that, of course, is just what a priori does. The additional work on the first pass of PCY is we have to look at each pair of items and hash the pair to some bucket and increment the count for that bucket. I want to remind you of 2 important observations about the buckets. Okay. First, if a pair is frequent, then the bucket it hashes to is surely frequent. Thus, on the second pass, the bit in the bitmap for that bucket will be 1, and we will surely maintain a count for this pair. Unfortunately, there may be many infrequent pairs that hash to the same bucket. These might be counted on the second pass as well. Okay. We can hope that at least one member of the pair is not a frequent item, because that will inhibit us from counting the pair on the second pass. But sometimes you will have a pair that is not frequent, but both of its items are frequent and it hashes to a frequent bucket. That pair will be counted on the second pass even though it is not frequent. It is also possible that a bucket will be frequent, but there is no frequent pair hashing to that bucket. Remember, each bucket's count is the sum of the counts of all the pairs that hash to it. But the only time that we have to count a pair on the second pass, and that pair turns out not to be frequent, is when the pair consists of 2 frequent items, and for one of the 2 reasons I've just mentioned, its bucket turns out to be frequent. However, we get a lot of leverage when a bucket is not frequent. In that case, we do not have to count any of the pairs that hash at that bucket, even if the pair consists of 2 frequent items. After pass 1, we set up pass 2 by doing the following. First, we construct the bitmap from the buckets. This bitmap has 1 bit for each bucket in order, so we can easily look up the bit that corresponds to a given hash value. 1 means the bucket was frequent, and 0 means it was not. And as discussed, if the buckets are 4-byte integers, we get a 32-to-1 compression when we replace the buckets by the bitmap. And as in the a priori algorithm, we need to create a list of the frequent items to use on the second pass. Our job on pass 2 is to count the candidate pairs. In the PCY algorithm, in order to be a candidate pair, ij must satisfy 2 different conditions. Okay. First of all, both I and j must have been found frequent on the first pass. For a priori, this is the only condition, and all pairs satisfying it are candidates. But the new condition is that the pair itself must hash to a bucket that was found frequent in the first pass. It is easy to see that if the pair ij is really frequent, then both these conditions will be satisfied, so this pair will be counted. Condition 1 follows from monotonicity, and condition 2 is satisfied because the count of a bucket is the sum of the counts of all the pairs that hash to it. That count cannot be smaller than any of the individual counts. We expect that each bucket requires only a small number of bytes. 4 is almost sure to be enough, and in many cases we can get by with 2 bytes per bucket. Okay. The reason is that it is sufficient to count up to the support threshold s, even though we said we should always increment the count when a pair hashes to the bucket. What we really want to do is, if the current count is less than s, then increment the count, otherwise leave the count at s. The number of buckets will be some reasonable fraction of the size of main memory, typically almost half or a quarter. The only time that would not be true is if there were so many different items that we needed all or most of main memory just to count them. In that case, we could not use the PCY algorithm. When we count pairs on the second pass, we have to use the tabular method. The problem is that the pairs that are eliminated because they hash to an infrequent bucket are scattered all over the place and cannot be organized into a nice triangular array. As a result, we should not use PCY unless we can eliminate at least 2/3 of the candidate pairs when compared with a priori. We're now going to introduce an improvement on PCY called multistage. This algorithm actually uses more than 2 passes to find frequent pairs. We'll concentrate on the 3-pass version. The benefit of the extra pass is that on the final pass, when we have to count the candidate pairs, we have eliminated many of the candidates that PCY would count, but that turn out not to be frequent. The 3-stage version begins with the first pass of PCY. The second pass, however, is a repeat of the first pass of PCY with a different hash function. The third pass has a stringent requirement for candidacy. The pair not only must hash to a frequent bucket on the first pass, but must also hash to a frequent bucket on the second pass. And on the second pass, we don't increment the bucket counts for just any pair. Rather, we only increment the count when the pair meets the criteria to be a candidate on the second pass of PCY. That is, it must consist of 2 frequent items, and it must have hashed to a frequent bucket. As a result, on the second pass, we get 2 benefits. First, the total count of all the buckets will be less because their sum excludes some of the pairs that appear in the data. That means it is less likely that a bucket will be frequent on the second pass unless it includes a frequent pair. But also, in the case that a pair is not frequent, it will only become a candidate if it accidentally hashed to a frequent bucket on both passes, not just one pass as for PCY. So here's a picture of the 3-stage algorithm. As I said, the first pass is just like PCY. Okay. The second pass involves features from both passes of PCY. On this pass, we store the frequent items, that's this, and we summarize the buckets in a bitmap as before. We use both these features to establish which pairs are candidates on the second pass. But in the multi-stage algorithm, we don't count pairs just because they are candidates. We just hash the candidates to another hash table using a different hash function. This hash table is approximately as large as the hash table in the first pass, depending upon whether the bitmap plus the list of frequent items takes up more or less space than the counts of all the items on the first pass. Okay, for the third pass, we maintain the list of frequent items and the first bitmap, but we also summarize the buckets of the second hash table by a second bitmap. And now we count all the candidate pairs, where to be a candidate you have to satisfy 3 conditions on the next slide. On the third pass, the candidate pairs are defined as follows. First, both items are frequent by themselves. This is the a priori condition for candidacy. And then according to the hash function used for the first pass, the pair hashes to a frequent bucket. These first 2 conditions are the PCY conditions for candidacy. And finally, according to the hash function used on the second pass, the pair also hashes to a frequent bucket. Here are 2 points about multi-stage that we should bear in mind. Okay. First, the hash functions used at each stage need to be independent of one another. Otherwise, each would report the same frequent buckets, and we wouldn't get any benefit from the additional stage. A common question about this algorithm is why we need the second condition, that the pair hashes to a frequent bucket on the first pass. After all, unless a pair meets the second condition, it's not hashed to a bucket on the second pass. But if we don't enforce the second condition along with the other 2 conditions on the third pass, then we can get an unnecessary candidate for the third pass. So consider a pair ij, where I and j are frequent, but the pair is not frequent. Okay. Moreover, the pair hashes to an infrequent bucket on the first pass. Now, it is possible that ij hashes to a frequent bucket on the second pass. True, in the multi-stage algorithm, ij is not hashed on the second pass and doesn't contribute to the count of its bucket, but there's still some bucket that it would have hashed to had we hashed it on the second pass. And that bucket might be frequent for reasons that have nothing to do with I and j. So we must test condition 2 along with the other conditions. Next, we're going to look at an approach called multi-hash. This algorithm is similar to PCY, except that on the first pass, the available space is divided into several hash functions. Now, this idea could be insane. Remember that PCI works if the average count of a bucket is much less than the support threshold S. That way, most buckets are infrequent, and we can eliminate a lot of pairs from the candidate set for the second pass. If we have the number of buckets, we double the average count. So suppose the average count for both hash tables is going to be over the threshold. Then almost all buckets are frequent, and you eliminate almost nothing on the second pass. But let's be optimistic. Okay. If PCY gives you an average count of 1/10 of the support threshold, then you can use 5 hash tables instead, have an average count of half the threshold, and each hash table will have mostly infrequent buckets. But now you have 5 chances to eliminate a pair that is not actually frequent, and the chances are very high that at least one of the hash functions will send it to an infrequent bucket. In that case, we get much of the benefit of 5 stages of the multi-stage algorithm, but we use only 2 passes and not 6. So here's a picture of multi-hash. We'll use 2 hash tables on the first pass, and the general idea, where more than 2 tables are used, should be obvious. On the second pass, the item counts are summarized as a list of frequent items, just as in PCY or multi-stage. But also the hash table from the first pass is summarized by a bitmap, as in PCY. Notice that the number of buckets created on the first pass is the same whether we use 1 hash table as in PCY, or 2, or any number. Thus, the sum of the lengths of the bitmaps is the same for multi-hash as it is for PCY, and less than it would be for multi-stage. On the second pass, we count the candidate pairs as always. The requirements for a pair ij to be a candidate pair is what you should expect. I and j must both be frequent items, and for each hash table, the pair must hash to a frequent bucket.